And off we go. Good afternoon, everyone, and welcome to this NEASQC webinar. This is our 8th of a series of 9 since last November. So I'm Pascal Bernier-Bruno. I'm the communication leader for the NEASQC project, and I will just share some practical information before I hand over to today's speakers. So this webinar is recorded, and you will get the link to the recording tomorrow. You will receive an email. It's in listen-only mode because we usually have a lot of people registered, so it's a bit complicated otherwise, but you can ask questions. You can use the Zoom Q&A panel to ask your questions to the speakers. You will also see the questions asked by other participants, and you can upvote questions or comment on questions. And the chat is also open for more informal exchanges, but I really recommend that you use the Q&A tool for questions. It makes it easier for the speakers. And now I hand over to Dr. Venkatesh Kannan, who arranged this webinar. Well, actually, he arranged also the other 3 webinars we're having in February, and he will be our moderator today. So, Venkatesh, the floor is yours.
Thank you very much, Pascal, and welcome everyone today for this webinar session. So as you see in the agenda today, we have 2 speakers, Dr. Andreas Wichert from the University of Lisbon. So he'll be talking about tree searches and how quantum computation is relevant there. And along with Andreas, we also have Dr. Vicente Moret Bonillo from the University of Coruña. And he will be sharing with us his work on inaccurate knowledge and quantum computing, which is also being addressed in the context of the NEASQC project. So before handing it over to Andreas, maybe a quick summary of what the NEASQC project is about. So the NEASQC project is a part of the quantum flagship projects. It focuses on development of algorithms and applications for practically relevant use cases. The consortium is composed of both industry and research partners, and we have teams of industry and research participants focusing on a number of use cases. This is a 4-year project that started in September 2020. And the use cases in this project are basically addressing chemistry-related problems for carbon capture drug discovery, for machine learning and optimization problems related to finance, HPC mesh generation algorithmics, and the series of webinars in February address the problems related to symbolic artificial intelligence and graph algorithmics. So today we have the speakers that are going to present topics that are related to the quantum rule-based systems and associated areas. So I welcome Andreas and Vicente, and I invite Andreas to start his presentation. Thank you.
Okay. Thank you for the invitation. I will start now this step. Other question, do you want to continue? Continue. Okay, wait a moment. Okay. Sure. Okay. Okay, do you see my screen?
Yes.
Yeah, okay.
Would you be able to turn it on to full screen mode if that's possible? To presentation.
It's not full screen modus?
We see the list of slides on the left as well.
List of slides on the left.
The thumbnails. We see the thumbnails on the left.
Okay, now you see the full screen?
Yes, thank you.
Okay. Okay, thank you for the invitation. I will speak today very short about research and quantum computation. Okay, my name is Andreas Wichert, and I'm from the Department of Computer Science and Engineering, Técnico Lisbon. Okay, so usually tree search is the most basic algorithm in symbolic artificial intelligence. It's the basis of most of symbolic AI algorithms. And first we will speak about uninformed tree search. So you have uninformed tree search where you don't have any information about the stage, about the way how to search, and the tree search is performed from initial state to certain goal states. Okay, so usually, as you know, maybe from AI, you have many different Tree search algorithm, the most known is breadth first search, where you extend it, you start with 1, 2, 3, 4, 5. Okay, you know it all from AI, symbolic AI. We have a formula. B is the branching factor. In this example, it's 2, and it's the number of expanded nodes. And this is represented by a geometric time series. Okay, so this is an example of taken from Nielsen, one of the first symbolic AI books, very known, 8 puzzle and the search. So you extend the states. So you represent the states of the puzzle game. It's not 8 puzzle, it's a little bit smaller to make it more simpler. And this would be the, for example, the goal states which we are searching. Deep first search is another algorithm, very easy. So instead of going step by step broad, we go into the depth. So we extend the first node, second, third, fourth. Okay, if we reach certain depth, we go backtrack and begin to search on the other branch. Okay. Deep first search doesn't require so much space to store the information. Again, deep first search, if we don't have a limit, can go forever. Okay, we have another example, a 3 puzzle search taken from the book for the deep first search. And then there is something in between, which is called iterative deep search. So in iterative deep first search, we will start with certain depth. So for example, the depth would be 1. So we extend only one branch. Then the depth would be 2, so we extend 2 branches. Okay, Z if we reach the goal. If not, we go back and search from the beginning. Okay, so we start with the depth 1, see if we search it. If not, we delete everything and begin to start with the depth 2. If we didn't reach it, we delete everything and start again. Okay. So one might think that this is a very inefficient search. Okay, because we always delete and search again and delete and search again. So naively, you can think that it's very inefficient. However, it has the same efficiency. Okay, so the iterative deepening search is the same as normal broad first search or deep first search. So we don't spend much more time. This is a kind of paradox, and it's explained that the number of the nodes grows exponentially at the last level, and this influenced the whole course of the search. Okay, it's a kind of paradox, but can be explained easily by a geometric series. Means the last number of the branching factor, which grows exponentially, is much higher than the remaining on and determines the search cost. So the search cost would be first 1 depth first search, 2 depth, and so on and so on. But the depth is only, okay, in the worst case, is only determined by the last search. Okay, so this were the called blind search strategies. Then what is very successful in AI is the heuristic search. Heuristic search, it's a kind of function which tells you which possible branch is better to go. So for example, in deep first search, we can go left, always left, 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 then right, left, right. Okay, but we can go also right, left, whatever. And when we have heuristic tells us, okay, either we go 2 or 3 or 2 this node or this node, and the heuristic would say, well, this is maybe a better choice. Okay, and heuristics is a kind of hint. It tells us choose this, follow instead. It's maybe something better. Okay, you heard, of course, about heuristic search also in AI. So the easiest way is you take deep first search algorithm, and instead going always to the left, you expand the nodes, compute the heuristic, and go to this node where the heuristic value is, okay, the best. Okay. This kind of search is called greedy best first search. Okay, greedy means your nodes have a certain value and you go to the better one. Okay, this greedy best first search doesn't guarantee that you really go faster to the goal. Okay, it can fail you, a heuristic can fail you. It's just a hint. It doesn't mean that it's always correct. Okay, and it also doesn't guarantee that you find the searcher's path. Okay, we have also another search algorithm which combines a heuristic search called R-search, which takes also into account the cost going from the start node to the node where we expand, okay, and the heuristic. And so we extend all the nodes and choose this one, which is the cheapest. There is also an algorithm which will also not speak, R-star search, where there are some certain consideration for the function GV that should obey triangle inequality. But anyhow, this R or R-star search guarantees that we find the cheapest way to the goal. Okay, it doesn't also mean that like the greedy search that we really find, okay, that the heuristic doesn't fail, that we really go in the right direction. In the worst case, we have to extend as many nodes as a blind search. Okay. Usually, to define heuristics function is very difficult. For example, we have some heuristics ideas for define the heuristics function for certain games, simple games, but usually, for example, if we perform symbolical mathematical computation or chemical manipulation, it's very difficult to define what is the right heuristic. Okay, we can try to learn them, but usually each domain, depending where we perform our tree search, our system has a different heuristics function. Okay, so it's very difficult to find a heuristic function. Okay, usually what measures the quality of heuristic, and the quality of heuristic is related to the branch factor. So if we have, for example, branching, branch means how many direction our tree we go. If the branch factor is 3, then if we compute, make the experiments and see that the heuristics improves the search in such a way that instead of having branching factor 3, we have approximately branching factor 1.5. Okay, so the heuristic can be measured, the quality of the heuristic, by many experiments in a domain and corresponding to the resulting branching factor. Okay. As we see in this example, okay, here we have branching factor 1 to 4. 1 doesn't make any sense because, okay, 2 makes sense. 3 and 4, and this is the depth of the search, and these are the corresponding values. So we see that the values begin to grow very exponential. For branching factor 4, branching factor 3 become very, very big. Okay. So these are the classical search strategies, which usually all the students learn in AI. So we've spoken a little bit about breadth first search, depth first search, iterative deepening. Greedy search means using a heuristic at one point. It's a kind of hill climbing, doesn't guarantee that we reach, okay, the fastest path. Then R-star search, and the other searches I didn't even mention, but they are related to R-star search. Okay. In the worst case, okay, the searches have somehow the same complexity, so they don't really guarantee us. For example, the heuristic search doesn't guarantee that we find faster the solution. Okay, it's just a hint, maybe. Or when we make some statistics, statistically we see that a certain heuristics in many, many examples give us an advantage, but in some worst cases, the heuristic can fail and can tell us some wrong direction. So that's why I thought, or we thought about how to use quantum algorithms like Grover's algorithm to speed up a tree search algorithm. Okay, so the idea is the following, very simple. We have a binary search or tree. This is the root. Okay, and these are the nodes expanded. So you can think we go there, there, there. And we can indicate, for example, each path by a certain number, 1, 1, 1, 0, 0, 1. So each path has a path descriptor, which corresponds to the binary number. So we can represent each leaf of the tree, of this very simple tree, by this kind of path descriptor. So this would be 1, 1, 1, 0, 0, 1, 0, 0. So it's binary numbers. Okay. So using this kind of representation, okay, so we will see these 4 numbers. We could use Grover search algorithm. Okay, so this would be the superposition. In this case, very simple tree will have 4 superposition, and we could use Grover search in the end to mark if something is a solution or not. Okay. Grover search, I think everyone knows. Okay, so this algorithm works only if we have a fixed depth. Okay, so if we have a higher depth, then we get more states. So the number of these strings grows exponentially with the depth. Okay, and we will use Grover's algorithm. And using the Grover algorithm with this kind of representation of tree search, it's called quantum tree search algorithm. Okay, and what is the speed up of the Grover search algorithm? As you know, the Grover's algorithm. Okay, this is Grover himself who invented the algorithm. Speeds up the algorithm quadratically. Okay, so it's square root of the possible states. So if we search a tree with a branching factor to the depth m, okay, so we get b power m different leaves. So the Grover search algorithm would speed up it quadratically, so the depth would be square root of this branching value. Okay, we can write also this as as the value b power m divided by 2 or square root of b power m. Okay, so the branching factor itself becomes much smaller. We can think maybe this is not much, but actually it's a lot. For example, we have again this representation of normal blind search tree, and the branching factor, square root of the branching factor, you see, doesn't grow so much. And if we, so here the highest number is 1100 somehow, but if we plot it in higher resolution, we see that it grows really, really exponential. But using Grover search algorithm, we using the branching factor 4 and deep search 10, which only required somehow 2,500 steps. So it's really allows us to perform a tree search algorithm, which was before not possible. Okay. And the other advantage is it's not really a heuristic. We are guaranteed that we find a solution. So we don't need to think about inventing any heuristic. We could just use the Grover search algorithm. If we have non-constant branching factor, for example, here we have maximal branching factor 5, then we choose for our representation this maximal branching factor. So some path descriptor will be just kind of rubbish. Okay, so now, until now, the Grover search algorithm goes until only certain depth. Okay, but we could use the idea of iterative quantum tree search to search for any depth we like. So we will search for the depth 1, depth 2, depth 3, depth 4. How do we do it? Well, we build an operator to the search, for example, depth 2, see if there is a solution, apply the Grover algorithm. Okay, then measure it and see if there is. If we see that it's solution, we are happy and we are done. If we see that it's just rubbish, no solution, then we increase the depth and we begin again to search. Okay, to a bigger depth, measure it, see if it's solution. If not, we increase and search again until hopefully we find a solution. Okay. So the result of the computation after measuring, we get the path descriptor, and the path descriptor tells us exactly in which branch, if we go left, right, or whatever, depending on the branching factor, this string, this number, either binary for binary tree. If we have a higher tree, we can represent it by different system. Okay, it describes us the solution from the root to the goal. Okay, if no goal is reached, then we increase it and search again. Okay, and we can continue, okay, forever until our computer resources are finished, or we don't like it anymore, or we find a solution. Using this Grover's basis methods and tree search algorithm, we can build, for example, any production system. Production system is something very essential in symbolical AI, which is based on tree search. So in production system, you have some rules which tells us how to search. And we have an initial state and a goal state. Okay, and we perform a search from the initial state to the goal state. goal state, okay. And in our case, okay, quantum production system, it's basically a quantum tree search algorithm. Okay, so the system would be composed of an oracle, which marks us the solution. Okay, it's a solution. If there is no solution, we don't get any marking at all, and we get some random state. Okay. Then each path descriptor describes the search. Okay, and the path descriptor grows exponentially to a certain depth. Now it's called T. Okay, so we start from the initial state, extends to a depth T, measure if it's a corresponding goal set. If yes, we are done. If not, well, we delete everything and build a new system with the depth T+1 and perform the algorithm again. Okay. Well, this is exactly what it's written here. We increase the search from T to T+1. Okay, there is some chart. Okay. Okay, no, do we have a library? Okay, no, not important as such, maybe later. And the quantum oracle itself can be built automatically, or the system can be built in theory automatically. While a production system is reversible, okay, can go forward and backward. We don't lose any information. Okay, we perform some kind of not really yet experience on a computer, for example, with a simple tree puzzle, like I showed you in the beginning, and describe it by a quantum circuits, or such a quantum tree search could be performed. However, we used a very simple and not really 8-puzzle tree puzzle because it's simpler, and we described it. Okay, you have only one rule: either go to the rotate in this direction or rotate in this direction. This can be represented by a binary tree where we have some path descriptor. Okay, so this is the depth tree, height tree, and we get different states. And our task is from initial state to go to a certain goal state. Okay, we can represent the states by certain numbers, the states itself, not the path descriptor. Okay, and by certain bits, so we can represent a state initial baud configuration, this one by corresponding bits, targets, baud configuration by certain bits. And our system is composed of 2 parts. Okay, we have a kind of black box, which is kind of oracle, which tells if we reach already our target baud, and an operator which generates new moves. Okay. Target measures tells us, did we reach from each superposition, did we reach the target or goal state, yes or not? Okay, and we have a control bit which tells us if it's 1, yes, we reach our target, if not, not. Okay, and we have an operator which allows us to generate all possible moves. Okay. We generate from certain goal state using the path descriptor, all possible states. Okay, we start. Okay, we have the certain depth which is given, and we extend it to a certain depth. Then we apply the oracle measure if we reach the goal state. If yes, okay, we perform the measurement. Okay, we perform first Grover algorithm. We perform the measurement, and we see if we reach the goal state and not. Okay, so this is depth of 1. So this is the move blank operator from the goal state, and we apply, okay, measuring, and we have the results. Okay, we can extend it for 2 depths, and we can extend the circuit for many depths. However, in quantum computation, we cannot really reset something. So before applying Grover algorithm, so this is the CNOT, which tells us, okay, this operator, if we reach the goal or not. Before applying the Grover operator, we redo the computation. We do everything backwards. So, okay, so there is no interference, and only then we perform the Grover operator on the corresponding supposition of all the states. Okay, this system, or this kind system, is equivalent to a Turing machine. Okay. Why? Because a Turing machine can be very easily simulated by a production system, speak also by quantum production system, by iterative quantum production system. Okay. And usually a Turing machine can compute forever, okay, the known halting Turing, and our iterative production system can also, in a sense, compute forever. Okay, it can never reach, like a Turing machine, which never stops. The iterative research or quantum production system can also extend and never stop. So it's equivalent. It's equivalent in the power to a Turing machine. Okay, and it gives you an advantage if you can perform some parallelization and speed up. It does it automatically. Okay, this papers or this work was developed with my PhD student Luis Tarataka, which is now in Brazil. And the main paper is described, or the simple paper, research and quantum computation. So if here you can download it or look at it. Okay. Then extending it to production system problems in quantum computation, the paper. And this is extending it using quantum iterative deepening. Means okay, these two papers describe a quantum system for certain given search. Okay, you have to specify the search in quantum iterative deepening. Okay, +1 journal, it's for free, you can download it. Well, we don't need to specify the depth, okay, because we extend the depth iteratively. Okay. And if you're also interested, I have written a book about symbolical artificial intelligence, quantum problem solving, and also machine learning. Okay, so this is the book. Okay, so thank you for hearing it. And if you have any question, do you have any question? Should I stop sharing the screen or?
Sure. Thank you very much, Andreas. I suppose please share your questions on the Q&A channel, and we'll come to them at the end together. So I'll hand it over to Vicente then. Thanks very much, Vicente.
No open questions. Okay.
Can you hear me?
Yes.
Okay, I will share my screen. Uh-oh. Vamos a ver. Can you see the screen, the full size screen? Hello?
Yes, yes, I can see it.
Okay, thank you, Takesh, for your kind presentation, and thank you very much to Pascal Vernier, who I know is in the background, taking care of all the technical aspects that these webinars suppose for her. I also want to thank the NEASQC project for the opportunity to meet exceptional people working on this exciting area. And my background is basically based on artificial intelligence, biomedical engineering, and quantum computing. I'm going to talk about the inaccurate knowledge from the viewpoint of the classical approaches, and I will try to expand this treatment, this classical treatment, by introducing quantum computing in order to see whether or not there is a relation between the classical models for inaccurate knowledge and the quantum computing, which is intrinsically probabilistic. I don't know why my slide just jumped. There is a sort of thing, there is a very interesting thing about inaccurate knowledge. There are some situations in which the information available is incomplete. The information available is not sufficient to make a categorical decision. The information we handle is not exactly true. the information we use is usually precise. There is a subtlety between uncertainty and imprecision, which we will address a little bit later. And normally, the real world is not deterministic. This is a very important thing, because quantum mechanics is not deterministic either. That leads us to that our model is often incomplete, and which is more important is that the lack of agreement between experts in the same field is frequent. What I mean with that? Well, there are some subtleties that when we work with inaccurate knowledge, and I will highlight some general concepts, like, for example, imprecision, that concerns declarative knowledge that are related to the facts, that means it's static knowledge. The uncertainty that concerns procedural knowledge or rules, that is a kind of dynamic knowledge. But there are other kinds of inaccuracy, like lack of knowledge, vagueness, belief or disbelief, that are intrinsically subjective. The question that comes up is that, is there any way to find the corresponding relationship between the classical and the quantum models? Because there is a fact which is a truth statement, is that humans normally achieve results without exact knowledge. They just make use of their common sense in order to reach conclusions. There are many models, for example, the probabilistic models. There are also certainty factor models. There are the theory of evidence. There are fuzzy logic models. There are plenty of models that can deal in a subjective manner with this inaccurate knowledge. I will focus on the certainty factors model because it has something to do with probabilities, which is a concept which is pretty familiar to all the audience probably. In 1975, Charlotte and Buchanan were working in the development of an expert system called MySyn that was constructed for management of the infectious diseases. And they started working with probabilities, classical probabilities. But they find a thing that is very interesting, is that when they studied the probabilities, they found that the same evidence can support simultaneously one hypothesis and the negation of this hypothesis, which in the mind of Charlotte and Buchanan, this was not acceptable. So they decided to consider separately, in a separate manner, that evidence that supports positively the hypothesis and the evidence that supports negatively the hypothesis, but based on the conditional probabilities and on probabilities. In fact, they defined two measurements that are the measure of increasing belief, which is a relative measurement that considers the increase of belief after the appearance of a given evidence, and they divide it by 1 minus the probability a priori, because when one evidence supports totally the hypothesis, the belief cannot increase anymore, so it has to be 1. In exactly the same way, they define the measure of increasing disbelief that appears when the evidence go against the hypothesis that is being considered. And if the evidence denies completely the hypothesis to be considered, the result of the measure of increasing disbelief has to be 1 also. The third situation is that when the evidence has nothing to do with the hypothesis, or we don't have enough knowledge to extract any conclusion. In that case, we consider that the evidence is independent of the hypothesis to be considered, and the measure of increasing belief is equal to the measure of increasing disbelief, and is equal to 0. In order to facilitate the use of the measures of increasing belief increasing disbelief, they define what they call the certainty factor. And this certainty factor, when we have only one evidence, is just a formal equation, because if the same evidence cannot support, as I said before, the hypothesis and the negation of the hypothesis. So if the evidence supports the hypothesis, the mission of increasing belief is greater than 0. And if the evidence go against the hypothesis, the mission of increasing belief is also greater than 0. But the other two, the opposite, are 0 always. Let me explain a little bit what I mean with that. Given a situation in which it appears one evidence, this evidence can increase the credibility, let's call it in this manner, of the hypothesis to be considered. In that case, the certainty factor is equal to the mission of increasing belief. And the mission of increasing disbelief remains 0. That doesn't happen when we use the probabilities. In fact, when we use the conditional probabilities, the conditional probability of the hypothesis given the evidence plus the conditional probability of the negation of the hypothesis given the evidence must be 1. And this is just denied by Shorrock and Buchanan. In fact, it can easily be proved that the certainty factor of a given hypothesis given an evidence is equal to minus the certainty factor of the negation of the hypothesis given the evidence. Let me go a little bit further on this, and we are going to talk about different evidence pointing to the same hypothesis. We have one hypothesis and we have a set of evidences that are connected with the hypothesis to be considered. Each of them with a certainty factor which applies on the arrow that connects the evidence with the hypothesis. Our problem now is to find a way of evaluating the certainty factor of the hypothesis given the whole evidence we have, we are dealing with. And for that purpose, Shorrock and Buchanan propose a very simple model in which if both evidences, I'm just talking about 2 only evidences to simplify the formulation. If both evidences support possibility in a positive manner the hypothesis, then the resulting certainty factor is the addition minus the product. That is consistent with the union minus the intersection. The same thing occurs when we have both evidences that go against the hypothesis, but the formulation changes the sign because we are multiplying 2 negative numbers. But what happens when we have one evidence that supports in a positive manner the hypothesis and the other supports in a negative form the hypothesis? The basic approach that was first proposed was just the addition of the two certainty factors. But if we take a look at this formulation, if we have 3 instead of 2 evidences, the model is non-associative, which was not fair for Shorrock and Buchanan. So in order to convert the model as an associative model, they divided by 1 minus the absolute value of this both certainty factors. Another thing which is interesting is when we propagate uncertainty. Uncertainty is related to the connections between facts. Here we have a differential network in which we have one evidence that is pointing to a second evidence that his time is pointing to a given hypothesis. And the propagation is defined like the product, the multiplication of the certainty factor of the hypothesis given the second evidence plus the maximum of 0 and the certainty factor of E2 given A1. And this is to prevent contradictory evidence. But when we are working in the real problem, this part of the inferential network, which is E1, E2, H, are in the knowledge base of our classical system. For example, if it rains a lot, then whatever. But when we face a given problem, we find that it doesn't rain a lot, it rains moderately, which is a sort of rain a lot, but it's not exactly the same. And Shockley and Buchanan decided to treat this kind of propagation between imprecision and uncertainty as a pure matter of propagation of knowledge. So the equation is exactly the same that we had before. And then they resolve the problem. The last aspect that we have to take into account, sorry, is that the evidences are connected through logical operators like is the and or the or.
Sorry to interrupt, Vicente, but the sound is really bad. There is a lot of, there is a kind of whining or whistling noise. No, I don't think it's your voice.
Probably. Let me check on that. What about now?
No, it's not really better.
It's better, it's understandable.
Yeah, it's better. Now it's better.
Okay. So when they use the logical combination of the evidence, the logical operator and is they treat it like a minimum, and the logical operator or they treat it like a maximum. So with the propagation of knowledge, the definition of the imprecision and the logical combination of evidence, they can manage the inaccurate knowledge, the whole set of inaccurate knowledge. This is all that I wanted to say about the certainty factor model. But let me face now with a classical problem. Assume that we have three rules, and B, which is connected with the hypothesis X. The second rule is X or C, which is connected with the hypothesis Y. And the third rule, which is connected with, which connects I and D or E with the hypothesis H, with the corresponding certainty factors. So we can translate that in a classical inferential network, like this one is a classical differential network without any problem. But the solution of this classical inferential network is just making explicit the equations we had before. But let me introduce now quantum computing. How can we translate this formulation into a quantum environment? Well, we will start first trying to reply the truth tables of the different operators we can find in a problem, in a given problem. For example, if we want to simulate in a quantum manner the classical node to obtain the truth table, we have to include a quantum line with an Hadamard operator, Hadamard gate, and a quantum node. Then we measure, and we project the result of the measurement, and we obtain the following result. We obtain 0 or 1 with a probability which is near to 50% in each of the cases, which is what we expect. If we go to the quantum AND operation, we need 3 quantum lines. And when we configure the inputs, and this is always kept 0 at the beginning, we configure the 2 Hadamard gates in the inputs, 1 Toffoli gate in order to perform the AND, and to reproduce the truth table of the problem, we need to make 3 measurements. 0, which is the result, and 1 and 2, which are the input of the system. We have several hundred of times the system that we can reproduce exactly the truth table of the AND gate 0, 0 equals 0, 0, 1, 0, 1, 0, 0, and 1, 1, 1, with a probability of 25%. I'm sorry, which is what we expect. I'm sorry. I really apologize. We also can have the quantum or operator, which is constructed from 3 quantum lines, 2 Hadamard gates, 1 Toffoli gate, and 2 control node gates. We proceed in exactly the same manner. I'm sorry. We have the same proportion, which is 25% in each of the cases, and we reproduce the truth table of the OR operation. What does it mean? That means that the quantum inferential network without imprecision and without uncertainty can be modelized by positioning properly the quantum gates in order to obtain the solution. And to put the system into superposition, we define the Hadamard gates just to reproduce the overall behavior of our system. We were talking about inaccurate knowledge. So we need to make a kind of transformation that allow us to represent imprecision and uncertainty.
We can't hear you.
You cannot hear me?
No, we cannot. The sound is very, very low. Besides the background noises.
I don't understand it because
Vicente, I believe
Yes.
there might be an issue with the mic. So we have very poor quality of audio input.
You have very poor quality of audio input.
No, we
Yes.
can't hear you, Vicente.
Back and start again, just in case.
We believe it might be the microphone on your
Yeah, I
earpiece.
think it's the microphone.
I don't just, let me check on that.
You could try switching to the microphone on your laptop if you have one.
Otherwise, I have a recording of Vicente's presentation. So if
Can you hear me now? Can you hear me now?
Very low audio.
very low.
Very low. That's amazing. Very low.
Shall I switch to the recording, Vicente, or?
No, we try to, because I'm finishing almost my
Okay.
talk.
Would you be able to disconnect the headset perhaps? Would that help?
Yeah, I think it's the microphone that's gone.
What about now?
We have a similar quality.
Yeah.
Similar quality, that means bad.
Quite, yes.
No.
No,
No.
no.
Would it be
So,
possible to disconnect your headset and
Yeah, we'll try again. Yes.
no, it's
Just-
getting worse, Vicente.
Just give me 1 minute.
okay. In the meantime, perhaps we can take the one question that we had for Andreas.
Yes, sure.
So the question, Andreas, you might also be able to see that in the chat. It was around if you have a library that would.
No, I don't have any library. We will develop a library, but not now, no public library.
Here I am. Can you hear me now?
Much
Yes.
better.
Yes.
That's great.
A good
Much
quality.
better.
Is a matter of the microphone.
It's
We
better.
have to-
It's not ideal, but it's better.
Okay. So I will connect my video.
Yeah.
I will upload the transparencies.
Please go ahead.
I'm sorry very much. Huh?
Oh, not at all, don't. Yeah.
Well, where is it? Compartir.
Can you find it, or do you want me to share
no,
it?
no, it's okay. I think it's okay. Vamos a ver. Maybe you can share my screen.
Okay. Okay. Give me 30 seconds to find it.
I have it here as well, Pascal, if you like.
Okay. So you were on slide 22, I believe.
Yes, probably yes. I don't see it.
It's coming.
Okay. So go previous slide, please.
Previous, yeah. Just a second. Where is my? Oh my. Oops. Yeah.
Yeah. Well, as we were talking about inaccuracy, we need to change the behavior of our inferential circuit in order to take into account the inaccuracy of the knowledge we are handling. For that reason, we define the inaccuracy matrix that takes into account the projection of the quantum state over the zeta axis in the Bloch sphere, where delta is an angle. An angle that is different in each case, depending on the imprecision or uncertainty that we are dealing with in each of the rules and in each of the chunk of knowledges. Next, please. So, if we are dealing with imprecision in the quantum inferential network, we have to substitute the Hadamard gates that appears like here by the inaccuracy matrix in the inputs, so that we can apply them to the Foley gate and obtain the output, and we continue developing the inferential circuit. And which is astonishing is that, next slide, please, when we compare the classical result obtained from subjective imprecision with the quantum imprecision way of dealing with the problem, we obtain that nice picture that shows an evident correlation, which is with a higher level of correlation. This is only taking into account imprecision. But if we consider the next slide, please. When we consider now uncertainty, we have to keep the inputs, the negation of the inputs, because the initial state is get zero, and substitute the Hadamard gates by the inaccuracy matrix in order to reproduce the behavior of the inferential circuit or the inferential network. And so when we compare again the results of this situation with the results of the classical approach, next slide, please, we find another beautiful plot of the results with a high level of correlation too. But I told you before that I didn't want to talk about the both situation, uncertainty and imprecision. And this is done through the inaccuracy matrix, but substituting all the inputs and the outputs, and the results are exactly the same fashion, the same way. Next slide, please. So there is evidence, empirical evidence, that the inaccuracy in knowledge, even if it's considered from the point of view of the subjectivity, has a reflection in the quantum approach for dealing with inaccuracy. Let me finish with last conclusion. Next slide, please. And the final conclusion is done by Richard Feynman in his wonderful conference that he gives in the United States. It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with the experiment, it's wrong. And we are going to develop, we are going to follow investigating the other models for treating with uncertainty from a classical point of view, and to see if there is a correspondence between quantum computing and the treatment of inaccurate knowledge from a classical viewpoint. And next slide, please, to finish. Thank you for your attention. And I'm sorry for all the inconvenience of doing my webinar.
Thank you very much, Vicente, as well. It was very interesting to listen to both Andreas and Vicente. Would there be any questions to either of the speakers at this stage? Please don't feel shy. Feel free to use the Q&A session there.
They're very shy today. Or our speakers were crystal clear.
Right, so we are almost on the hour. I'd like to ask if Andreas or Vicente, if you have any additional comments.
Maybe I have a question to Vincent. Can I?
Sure,
Yeah,
of course.
Sure.
What would be the application of this approach which you described? Why is it of an advantage?
The advantage is just a matter of increasing knowledge, because in my opinion, nature behaves always in the same way. For example, transition of states. always follow the same laws in a different manner, but the same laws. And I'm pursuing a method of making hybrid systems between classical computing and quantum computing, taking the advantages of both approaches in order to improve the performance of the whole system that we can develop. Of course, there are a lot of things to do before, but I think that these preliminary results we obtain pave the way of a path that we can explore, and which is really very funny to explore. Because which is difficult to understand is that the current model for dealing with uncertainty, probably without considering the probability theory, are subjective. But humans do perform conclusions with subjective knowledge. And we need a framework to put it in a strict manner, in a mathematical manner. So I do believe that quantum computing can help in this point, in this line, in this direction. I'm not talking about quantum supremacy, at least by the moment.
Thank you. Can I ask another question? Can
of course, please. Yeah.
Okay. Why do you think people stopped using certainty factor calculus and they're using mostly Bayesian networks? So nearly no one is using any more certainty factor. Do you know why?
My opinion. The certainty factors model has an inconvenience, which is that it's an ad hoc model by nature. There is no solid mathematical background. That is from the point of view of the developers. But from the point of view of the users, the certainty factors model is a very easy model to understand. And so, from the point of view of the applications of the model, of the theory of the certainty factors, it's very simple to say this is high, this is low, this is medium, this is whatever. I was working a lot of years with medical doctors, and they appreciate very much to not, they don't need mathematics to explore their beliefs. But just say yes or no, it was enough. And this is very practical from the point of view. Then appears Julia Perron and use Bayesian networks and formalize the model. But there is, for me, a pitfall in the Bayesian networks model, which is that you need a knowledge model between the mathematical treatment of the information you handle. Building an inferential network, a Bayesian network, is something which is not trivial. We have to study all the dependencies of and conversely, this is a much simpler model. This is why we use it at the beginning. We acknowledge that the model is not being used anymore, but I treat to find the correspondence between the probabilities used in the certainty factors with the probability related to the quantum computing. But this is just a way to start working on it. Evidential theory is used today. And Bayesian network is difficult to write.
Okay, thank you.
Thank you to you.
Thank you very much, both. So if there are no further questions, then I'd again like to thank both of our speakers very much for today. It was very interesting. We have, as a part of this series of webinars in February, one more next week on the 21st of February, and that would be on the topic of probabilistic safety assessment enabled by quantum computing. So I thank everyone again. Pascal.
Yeah, I don't have anything else to say. I mean, you've said it all, Venkatesh. Thank you, everybody. Thank you for your patience, because the background noises were painful. Thank you for staying until the end. And we'll get a new mic for Vicente next time, I promise. Thank you, Andreas. Thank you, Vicente. Thank you, Venkatesh. And we hope to talk to you next week. Thank you. Bye-bye.
Bye-bye. Ciao.
Bye, everyone.
Yeah.